Welcome to Spring LIB.
So let's call a1, a2 all the way to an the first n non-square integers. So to make an example, let's write the first integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so forth. Okay, so 1 is 1 squared, so it's not a1. 2 is the first non-square number, so let's call it a1. 3 is not a square, so it's the second non-square number. 4 is 2 squared. Then 5, 6, 7, and 8 are the following non-square integers. Then 9 is 3 squared, and 10 is a7, and so forth. So let's fix n. So the numbers from 1 up to an are all the non-square numbers all the way up to an, and the squares that we've skipped. So 1 squared, 2 squares, up to k squared, where k squared is the last square right before an. For instance, if n is 7, we're looking at the 7th non-square number, which we know is 10, and therefore we have 2, 3, 5, 6, 7, 8, and 10 as non-squares, and we also have some squares. The squares are up to a7 are just 1 squared, 2 squared, and 3 squared. So k squared is 9. Now the last square before an is by definition the number k, such that k squared is lower than an, lower than k plus 1 squared. Now what is the value of an? That's exactly n plus k, because up all the way up to an there are the numbers a1, a2 all the way up to an, and those are exactly n numbers of those. And then there are the squares that we skipped, and those are exactly k. So the value of an is n plus k. For instance, if n is 7, as we said above, a7 is the number 10, and the number 10 is exactly n, which is 7, plus k, which is 3. So to finish the proof, we just need to show that this number k is indeed the closest integer to the root of n. So we rewrite the equation that we had before, so k squared lower than n plus k, lower than k plus 1 squared. But n plus k is an integer, so it must be greater or equal than k squared plus 1, because it cannot be k squared, and the next integer is k squared plus 1. And again, it must be lower or equal than k plus 1 squared minus 1, because it's an integer and it cannot be k plus 1 squared. So the maximum value it can be is k plus 1 squared minus 1. So now we subtract k from all the terms and expand the products. So we have k squared minus k plus 1 is lower or equal than n, which is lower or equal than k squared plus 2k plus 1 minus k. Now we complete the squares. So here we have k minus 1/2 squared plus 3/4, lower or equal than n, lower or equal than, and similarly this is by completing the square, k plus 1/2 squared minus 1/4. Right. Now the observation is that on the left hand side, that is definitely greater than k minus 1/2 squared, because I mean it's that plus 3/4. And on the right hand side, that's definitely lower than k plus 1 squared, because it's that minus something. So by reading the green parts, we see that k minus 1 is lower than root of n, which is lower than k plus 1/2. but this means by definition that k is the closest integer to the root of n, which is what we wanted to show, because now an was, by the previous slide, n plus k, and we said that k is brackets of root n, and that's the claimed formula.